Now we can start talking because I just start. Options we have today because of spring break and because of the nature of how the topics have landed. I'm not sure. Let's see. First off, I get this out of the way. Make sure we record everyone that's here. I know. Also wanted to make sure I got it's fine. My spring break is okay.
Yeah. Thank you.
That's why we can't have nice things. Okay, so one thing that we can do, I can. What class is? Who's your professor? Don't tell me it's me, right?
Dr. Rico, but
Rico.
not anymore.
Mark.
Okay, you have a Dr. Oil?
Yeah.
Okay, cool. I have their exams.
Okay.
And we could work through problems that we just did on the exam, but I don't know if that would make you nervous, right? If you didn't do it, right?
Yeah.
I don't know. It's up to you, all right? This is just suggestions, just to let you know. I got copies of their exams, and I can work through problems if you want. Well, you've already taken the exam, right?
Yes.
But I think there's actually somebody in your class that hasn't taken the exam.
Oh, really?
Yeah, so I don't know if Dr. Rico, or I guess me, I guess I'm the one that does it, but we're also kind of like in the middle of topics right now, because I think you guys have probably, I think have you started angular velocity? Was that the last thing you guys had, angular velocity? Did you start velocity?
Is that the one on this?
Yeah, that's the, yes, that is the, what do you call it? Is that today's homework? Is that the one that's due?
Yeah. It's
Okay.
due when we came back from the.
Yeah.
Yeah.
So, so does that also due when you get back, or was it already due?
We haven't covered general plane motion and absolute and relative velocity yet. We covered translation and fixed axis rotation.
Okay. All right, cool. So I think we're on the same page. All right, so we could do some problems related to that, because there's really only two example problems related to that. This guy right here and this one right here. This right here requires the general plane motion, right? So you guys haven't done that yet.
No.
This right here and this right here.
Yeah.
Problems that could be,
Yeah.
but the ones where we have rotation, we can do that. So we can cover some of those if that's what you want to do.
Yeah, I'm fine.
One of the things that I noticed is that he actually assigned the problems that were supposed to be the extra problems. So he's stolen some of the problems that could have been done. Made my life difficult. Well, that's all right. I don't mind. So reading is hard, but a cord is wrapped around the wheel in figure 16.6, which we presented that, is initially at rest when theta is equal to 0. Come on. I think it has to be pulled out. No? Maybe this goes all the way down. I haven't done this in a while, apparently. That way? I think you have to come out and pull outwards. How come it's not coming back up? I'm having a case of the incompetence. Gonna come all the way wall. There you go. That was way harder than it should have been. And okay, so that's when theta is equal to 0. If a force is applied right here to the cord and gives it an acceleration of a is equal to 4t, so we see that acceleration is a function of time, where t is in seconds, determine as a function of time the angular velocity of the wheel and the angular position of line OP in radians. So unfortunately, I never like problems that don't actually have a numeric answer. It's like unsatisfying. It's just unsatisfying. So let's put some numbers in there. Let's say find the angular velocity when after 1 minute, 60 seconds, and the angular position of line OP. All right, so there you go. So when you see that the acceleration is equal to 4t meters per second squared, and if a force is applied there, and they must be talking about this spot right here, so that acceleration right there. So on this wheel, we're thinking about an acceleration there. That's the acceleration. You agree? So this is like very similar to velocity. Can be treated this way when we're talking. This is a tangential velocity acceleration. So it's going to be like alpha times this r. Alpha times r is going to be equal to 4t now. So, because the radius of this is 0.2, we'll go over here and say 4 divided by 0.2 t, and we're going to say, well, that's going to be, I have it on my page that it's equal to 20t. All right, so this is going to be radians per second squared. So now we want to find the angular velocity. So this goes right back to the fundamental kinematic relationships, where alpha is d omega dt, right? Which, by the way, is the same thing as saying theta double dot is equal to d theta dot dt, right? So make sure that you're feeling comfortable with the fact that we will, sometimes it seems randomly, just jump between alpha and theta double dot and omega. Hello. Here again. So you were never here if you don't put your name in there. Yeah, we will just sometimes seemingly randomly swap between alpha and theta double dot and omega and theta dot. So just recognize that. But just like we did in class 1 of the semester, we can rewrite this thing to say that d omega is equal to alpha dt. And we can plug him in there and do our thing. Right, they say starting at rest, so that's kind of good right here. So there's going to go integrate from 0 to omega, and then integrate from, it's going to start at time 0, and then inside where alpha was, we could put 20t dt. Start back up here. So we get omega equals, and 20 over 2 t squared, and because we're just going from 0, so all right, we're good. 10t squared. We can keep on going. All right, so that was what the original problem said, but then we go at t equals 60 seconds. We can say that omega, put him in here, figure out how fast he's going. And I had it in my coat, that's why. My calculator. I don't like using my phone, I like using my nice, Hewlett Packard calculator. Oh, so nice. Oh, that makes me feel superior to everyone. That's a weird thing to say out loud. 60 squared. Losing it. Where am I? There you go. Boom. Times 10. Oof, wow, that's a lot. 36,000, so I picked a weird one, radians per second. I don't like radians per second. I don't have a feel for what that is, but I know what an RPM is. Picture that, how many revolutions per minute. God, the second is just too fast, it's moving too fast, so I don't know RPM, so I can figure what the RPM is. So we know that's going to be 2 pi, yeah, that's right, 2 pi radians per revolution, so we want to divide by that, and then we need to multiply by 60 seconds per minute, right? And that's going to get us, so our omega can be multiply by 60, divide by 2, and divide by, so we have a crazy large number, if I did that right, but I'm feeling like I didn't. RPM. So that was a ridiculous thing. So I picked a really bad time for 60 seconds. It was like way too many. But let's keep going anyway. Doesn't matter. The angular position of OP in radians. So we're going to do the same thing that we did over here, but now we're just going to take our fundamental kinematic equation and say that we have omega is d theta dt. And therefore we can write d theta equals omega dt, and then integrate d theta. Starting at, they said it's 0 degrees? 0 degrees, yes. And we're just gonna go to theta, I guess there, and then integrate and stick this in here and go 10t squared dt, and we're going to go from 0 to t. So we're going to get theta is going to be 10 over 3 t cubed. So at t equals 60 seconds, that's going to be some weird damn thing, right? We could say that theta is 60 cubed, and so 720,000 radians, which don't mean anything to me. So let's go ahead and divide him by 2 pi radians per revolution, and then it'll make something make sense. You see that it goes a lot of revolutions. 114,600 revolutions. That's weird. That's a large amount. So I'm not feeling as though that was like an exciting problem. Didn't capture your imagination. Didn't make you excited. I guess the thing we want to get back to is like, that first thing in class where we're talking about these fundamental kinematic relationships. But now we're just going to do them in terms of angles instead of translation. So here's another one. A motor shown in the photo. Actually, there's not a photo there. I didn't bother with putting the photo in there. I put the figure that was near the photo. So it lies. It's a liar. Let's see if we can see that a little better. Oh, don't start with the screen again. Okay. Well, I used a lot of black in that problem. So the motor shown in the photo is used to turn a wheel and attached blower, I guess, if you say so. The details are shown in this figure. That's the figure we're seeing. If the pulley A connected to the motor begins to rotate from rest with a constant angular acceleration of 2 radians per second squared, determine the magnitudes of the velocity and acceleration of point P. See, that's on the bottom right there. on the wheel after the pulley has turned 2 revolutions. Assume the transmission belt does not slip on the pulley, right? So, a bunch of different things we could do to start. Maybe I'll follow along with what Mr. Hippler did right here, is figure out what theta is going to be, or we can say what delta theta is going to be of A. All right, so I need to go back here for a second and reread this. Determine the magnitudes of the velocity and acceleration of P on the wheel after the pulley has turned 2 revolutions. Okay, so I think that guy up above is the thing that turns 2 revolutions. Do you agree? The pulley, that's what they mean, the guy up there at A. So I just want to double check, right? So we get 2 rev times 2 pi radians per rev. And we get 12.57 revs. So much of dynamics problems are reading the problem. Okay, so we want to try to get some clues on how to approach how to approach the problem where we want to go. So we're not given any time. Did you notice that? There's no time involved. And we are told that it's constant acceleration. And we are looking at, and we're given the acceleration, and we need, but we know a change in position. What kind of equation, what equation maybe should sort of drift into your mind like, hey, I think that's the one. I don't even know what to call it. I call it the wild card. The wild card equation. Have I mentioned that one before? No. If we had like a ball that was coming up that fast right there, and we had this distance that we were going to go, like a delta y, and you knew that gravity was pointing down that way, and you knew the velocity here, and you want to know the velocity up here, how would you get it? By the way, you could say work energy, you know, you'd be right, but that's not really, I just want kinematics.
Would it be V final squared is equal to V naught squared?
Exactly.
Minus 2A, well, 2GH?
Yeah, that'd be right, yep. And then the delta y, yeah. That's the same thing that's going on here, right? I think sometimes for students, the angle thing makes it seem, it's hard to like get that, like this is the same thing as that, right? So now instead, we would go omega squared is equal to omega, and this is going to be whatever this is, 2 alpha delta theta. Does that make sense? So you just want to kind of like feel comfortable with the sense that, you know, okay, it's not really any different. It's just the angle kind of like equivalent of the thing. So what we could do is after 2 revolutions, we could find what the pulley, right? So omega A squared is going to be equal to omega A. It starts from rest, so it doesn't really matter. But I want to write the equation correctly. Alpha A and then delta theta A. So 0 squared plus 2, this is 2, and this is 12.57. So we should end up with omega A equal to 7.09 radians per second. All right, so now we want to, easier to draw these things, to think of them through, but many of the problems will have as their main thing underneath the hood is this idea that if this thing is rotating, let me color code this. if that's omega A, then this spot right here, VA, is going to be equal to omega A times RA. You're okay with that? And so, because the belt is moving without slipping, right? This spot right there is moving at that same speed. And therefore, this spot right here is moving at that speed. And therefore, this guy, we can call him omega, what is this thing called, B? Omega B, it has that same velocity. So that's also going to be equal to omega B times RB. We're okay with that? So what we could find is that omega B is equal to RA over RB times omega A. So what, 0.15 over 0.4 times 7.090. That's supposed to be a 9. Doesn't look like a 9. Looks like a smudge now. .659 radians. But the same thing is going to be radians per second. I don't know, put radians. Radians per second, sorry. Get back here. Same thing can be true. Alpha A. It's going to create a tangential acceleration that will also be equal to what the belt is happening right there, because there's no slip. And that's going to be alpha A times RA. But it's going to get down here. And that's going to, and it's going to be the same value as above, so that's going to cause alpha B. So it's going to be equal alpha B times RB. And therefore we'll have alpha B is RA over RB, alpha A, or 0.15 over 0.4 times 2, right? They told us 2. And I think it's 0.75 radians per second squared. And we have to go back up to the top and say, determine the magnitude of the velocity and acceleration of point P. Right? And they use the word velocity, so they don't mean speed, but they say the magnitude, so I guess that is speed. Yeah, they say the magnitude, so they do mean speed. So VP is going to be omega B times RB. And we just got that, so we have 2.659 times 0.4. And That's 1.06 meters per second. So that's one of our answers. The next is a trick, a hidden trick. They're trying to, you're gonna be lulled into only doing this. Acceleration of p in the tangential direction is alpha b rb, or 0.75, 0.4, a pretty small number, right? Well, they really, I think it probably turns to just 0.3, but I'm gonna give some zeros in there. And this is meters per second squared, but we're not done. Why aren't we done? What's the trick? It's not all of the acceleration. It's not the only acceleration there. Let me off talk. Let me off talk. What other acceleration is going to happen on that wheel? Centrifugal, right? Remember, I'm going down the highway, minding my own business. My velocity to the left is 0. But then I start to take a turn around a curve. Now I have velocity to the left. I went from nothing to something. So anytime I'm going around a curve, I have to accelerate towards the center. I don't have any choice. Same thing true with this guy right here. As he's moving on. He's got no worries in the world. Just going wrong. But then as soon as he starts to get right here, he starts to change his direction. So he has to accelerate. So down here, he's accelerating in that direction. Hector, just remember that one. It's easy to overlook it. That we're also going to get the acceleration of p in the normal direction, which we can write in two separate ways. We've been used to writing that normal acceleration is this, v squared over r, or rho, if we want. But recognize that when we have something like this in circular motion, that the velocity is r omega, right? So therefore, we can have omega squared r is the same thing, right? Omega squared r is the same thing as v squared over r. So feel comfortable with that? If you want like a little hint, we could go back to particles and polar coordinates. Remember the acceleration in polar coordinates? We could write it someplace where it won't hurt our brains to go back to that bad time in our life. We had r double dot minus r theta dot squared, er plus r theta double dot plus 2 r dot theta dot, e theta. If we go right to here, r theta dot squared is the same thing as this, right? It's omega versus theta dot, same deal. So just, I think making those associations, I hope it's not too much information, but maybe it can help kind of ground it, make you feel more comfortable with it, so that you would just come up with it on your own. Omega b squared times rb is going to be equal to, what do we say, 2.659 squared times 0.4, and that's going to be a larger number. And a lot of times when you're doing this, like this one gets to be so much larger than that one that this one doesn't even matter into the answer. And I think that's the case here too. So in order to answer their question, we need to take the square root of 0.3 squared plus 2.827 squared. And it doesn't really change the thing too much, it just goes 2.84 meters per second squared. So there's your answer. And these are pretty similar to your homework problems. They might just have, you might just have to do it a couple more times with like the second problem where there's gears, right? You have to look at it and just go bang, bang, boom, and recognize the middle one that they have the same angular velocity and the same angular acceleration because they're stuck on a shaft together. Well, I'm out of problems unless you want to pre-learn some of this. We could pre-learn some of this. I don't know if you really want to. We could, but that's like taking a class. We're not taking a class. This was supposed to be a help session, like extra things, kind of like. But we should have more of a conversation. How about looking at the exam? Do you want to look at the exam? No.
The one we just took, or?
Yeah.
Sure.
But it's gonna make you feel bad though, because you're not gonna see the grades. So now you're gonna be like, oh, I should have done that. Oh, I should have done that. Oh, I should have. I can see that. I don't know. Depends. And it doesn't help you now that you already took the exam, right? But you might learn the thing. What's that?
You can do some of that.
You want to do some more of this?
Yeah.
We gotta pick a problem on a book then.
Okay.
Let's see what we got. Does this thing even work anymore? Let's see, maybe it does. It's like all hidden up here. I like these little things, but I don't know if other professors. I just wish the board was bigger, or the projector was bigger. If I was gonna use this thing. It also keeps me anchored to the desk. Maybe that's a good thing.
On the exam, that question with the impact, I think it was like a concept. It was like if the diagram is complete or not.
Oh, that was Dr. Rico's exam.
Oh, okay.
Well, no, I have it here in front of me. I think it says. So one problem is that I think on these, she was, she has a student hasn't taken it yet. So I don't know, but we're making a video. Do you think the student's gonna watch the video? Do you think she's gonna give him the same exam? Anytime someone's missed my class, my exam, I give them a totally different exam. Yeah. I don't want to encourage that. Yeah. I can't prove that they're not faking it, but I did have one student that missed all 3 exams, every time, sick every single time. I just give them a different exam. What do you do? Yeah, it's a lot of work on my part. In order to receive full credit, state whether it was true or false and support your answer with a few sentences. The figure below is correctly labeled. The line of impact should be normal. Sorry, if you didn't get it right.
I thought it was missing the impulse arrows.
But that wasn't on this problem. This is what you're talking about, right?
I think so. Maybe I just like read it wrong. Yeah.
It was because she had that as N, and then it's T, right? That should be N, and that should be T.
Oh, okay.
Yeah, the line of impact should be in line with the centers of the things.
Oh, okay. Yeah, it's 5 points.
You know what's messed up is that that was the day that I taught class, right?
Yeah.
So that was my fault, wasn't it?
Oh.
That you didn't learn it.
Maybe.
If we were assigning blame, we shouldn't assign blame. Come on, man. Don't hurt me like that.
I found your videos on YouTube and I was like watching them.
Did you watch to the very end on some of them? No, actually, it's because after COVID was spring break. COVID was spring break in spring 20. So we all went fully online, and that's where I started making videos like a madman. And then so I had half a semester with the videos, so I actually said, well, you know what? I'm gonna record all of my examples and stuff. And I think there's actually one missing. I think there's one where there's not enough stuff. I think it's actually class 13 actually. I think maybe class 12. But anyway, I started getting like, I started playing guitar at the end. Just to see if anybody would notice, and no one ever has. What am I doing here? I'm on camera. See, I opened up the wrong thing. Camera. There you go. This is going to be such a great video to watch this one. Okay, you can't decide. Oh, there you go. Let's see, we are in chapter, actually this might be the right chapter. Yeah. But we're section here. So let's see. Let me clean up the board a little bit. I don't know, maybe I will. I don't know what I'll do. No one has to have the book with them. They can read along. We can pick a book. This is a good book. You should own this book, by the way, if you don't own the book. If you don't own the book, don't tell me. I don't want to know. It makes me sad. So I have a student in one of my other classes who is borrowing my book. I didn't even realize because he's borrowing my book. I had him for last semester, and we used the book in both semesters. And I had like open book exams, so you have to have the book, right? But he borrowed my book. I totally forgot about it at the first exam last semester. And another student says, "My book hasn't come in. Can I borrow a book?" And I'm like, "I don't really." He goes, "He's borrowing your book right now." Like, just threw him under the bus. Just totally threw him under the bus. He's borrowing your book right now. And that guy's my advisee. Oh. So I can't even like turn him into his advisor and say, "He doesn't even care enough about this class to buy the book." I just want to point out to students who don't buy the book, think about your money. Is being paid, or you're paying, or someone is paying. Someone's paying that money to take college classes, but then you skimp on the book. I know they're expensive, but I mean, the difference between a B and an A. I'll tell students, like, you know how much you would have to bribe me to change your grade from a B to an A? I don't know. I would never do it. So that's a lot of money, right? But then think about how you could turn a B into an A by buying the book. Doesn't seem that expensive now, does it? Yeah, I use bribery as a means of explaining things. All right, so we could pick up one of these examples. Sometimes professors use these in class. So, and I also pimping out the book here, saying, hey, solving problems on your own, this is a great section. When you started homework, a lot of times when you start homework, you look over these examples right here, kind of trying to find one that kind of get you in the right spot. Understanding, okay, yeah, that's similar. Or you work through it. It's actually, instead of reading it, sometimes it's better to, you could actually be more efficient to do homework this way. I swear it is. I swear it's true. You put your hand over the thing. Try doing this problem. Yeah, you might not get very far, but then you take a peek. Ah, I got it. You actually, that's the learning process where you actually learn, right? Cover the thing up, try it yourself. That's how I learn. It's how I'm teaching dynamics. How did I learn dynamics? Well, I learned it in college and I quickly forgot it. Quickly. I never used dynamics, not even once, ever, in my job. Not a single time. But dynamics helped my brain turn into the kind of brain that could solve problems. That's the usefulness of the class. But also dynamics is, I said this yesterday in class again. I repeated this. Dynamics is the most important topic in human history. That's bold. Now I've said a bold thing, I got to defend it, right? Think about how we got here. Bunch of shepherds, stargazing, looking up at the stars, and asking questions. Why do these planets and stars move the way they do? And then you had a bunch of people that, wanted to get some food, and they took a rock and they threw it at the food, and then they aimed wrong. This is the first kinematics problem, And then they proceeded to try to solve that problem. And we eventually got F equals ma out of that whole deal. Newton. And by the way, they called it philosophy back then. It was philosophy. And that was, but then they were able to come up with laws. And they were able to prove those laws. And it was the first time in human history that they came up with a hypothesis for why something worked. They developed it, they wrote a law down, and then they were able to defend that law and prove it right. The first one. All the others, oh, okay, chemistry, we're going to go that same process. Biology, we're going to use that same process. The scientific method. Start out with dynamics. Most important topic, human history. All things spring from it. Now does the class seem important? Sorry, I just looked at it. So I read that in a book, by the way. I didn't come up with that one. I should footnote that, but I can't find the book. I own a book somewhere. All right, so let's. We're gonna try to find a problem. See, you can see. Ooh, that looks familiar right there. That problem. I've asked this problem before. Let's just do this problem right here. Let's see. Can we? I don't know. Can we find something that's complicated enough, but not too complicated? Let's do problem 1528. A plastic film moves over 2 drums. And I wish we could get in focus. There we go. During a 4-second interval. The speed of the tape is increased uniformly from 2 feet per second to 4 feet per second. Knowing that the tape does not slip on the drums, determine the angular acceleration of drum B and the number of revolutions executed by drum B during the 4-second interval. All right, so let me see if I can write down a lot of this important information here. Yeah, I actually got that to work. So I like to draw these things out for myself. Didn't do a great job of that. Let's make it pretty. It's not pretty. It says VO. And this is 15 inches. And boom. This is 9 inches. And VO. Okay, so it's not slipping. And we said during a 4-second interval, it goes from VO 2 feet per second to V1 4 feet per second. And the delta T is equal to 4 seconds. I always think this problem's too easy. What do you think? We want to find the angular acceleration of B and theta B, right? Delta theta B. But we want them in revolutions. Oh, they're tricky. How do you think we start? First off, do we do anything with A in this? Are we using A at all? I don't think we need A. Huh. Plastic film moves over 2 drums during a 4-second interval. The speed of the tape increased uniformly, so constant acceleration, from 2 feet per second to 4 feet per second. Knowing that the tape does not slip, determine the angular acceleration of B. I think A is totally unneeded, because that velocity right there, really we're just looking at this to this, right? So he's going from 2 feet per second to 4 feet per second. That's supposed to be a feet, right? So for one thing, we could do this in several different ways, right? We could just figure out what the angular velocity is going to be. Maybe that's a good idea. Let's figure out what the angular velocity is going to be. So right here, the angular velocity initially, here's your angular velocity after. Initially, it's going to be v over r. So 2 feet per second multiplied by 12 to get it into inches per second, and then divide it by the radius, which is 15. They must use this figure later on in another thing, and then you need a. Because usually they'll say that if it's used for multiple problems, they'll have it underneath the thing. But that puzzles me. Radians per second, and then omega 1, v1 over r. I guess these are b. That should probably be b0 and b1. We go, it's just going to be twice that, right? So 32. Radians per second.
Dr. Deal?
Yes.
How did you get 16 radians per second? Should 24 over 15 be like
1.6?
okay?
Because I was talking instead of thinking. I was told as a young man I did that by my dad. Think before you speak. I like the other way around. So anyway, we want to get the angular acceleration. This is really kind of silly, but it's just going to be alpha is going to be delta, right? Delta omega divided by time. So 3.2, 1.6 divided by 4. Right? So 4 seconds. So 0.4 radians per second squared. But this is actually would be a much better problem as far as a teacher is concerned if we only ask part B, because we're actually kind of walking you through it, right? If I only said the number of revolutions that it will make in that 4-second thing, we could do that in a couple different ways now. We have 2 choices. One is to go theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. So we can assume that it starts at 0. We're going to go delta theta anyway, so might as well make theta 0. Starts off at 1.6, goes for 4 seconds, plus 1/2, 0.4, and then 4 seconds squared. Underneath it. And say 16 times that divided by 2, 4, and 1.6. We get 9.6 radians. divided by 2 pi radians per rev. And you get 1.528 radians. The other way that we could have approached it, let's take another color. We haven't been kind of green today. So, alternatively, we could have gone omega squared is equal to omega naught squared plus 2 alpha delta theta, and we had 3.2 squared equals 1.6 squared plus 2.4, and then delta theta. .2 squared. Let's see if it's true. I could have screwed it up. If it's not true, I screwed it up. Subtract it out. Divide by 2. Yeah, 9.6 radians. The important thing in this type of session, right, is when we're doing the examples, is to ask the question, how did you know to do that? Or to demonstrate the thought process. You know, like how'd you go about reading the question? How'd you go about, you know, what was my process? Your process might be different a little bit, but I think you could adapt my process. First is reading the problem, right? Breaking it down. I think drawing this, even if it's repetitious, and you don't like your own art thing, just do it anyway, right? And because it's a good habit. So because then you're thinking, as you're drawing the thing, I'm thinking. I'm trying to process what is being asked. I'm reading the sentence. I'm not a good reader, right? So it's hard for me. I'm a visual guy, so maybe it's different for you. Maybe that you're more of a reading, you know, that helps you to figure. I need the picture. I need the act of drawing, and then I need to write down what it is I know, and then maybe make like a little figure over here as I'm, you know, trying to piece together, and then they go, oh, I know how to do it, right? That's the aha muscle. That's why dynamics is an important class. Because it's this opportunity to exercise this aha muscle in a way that's very analogous to all engineering courses, right? And there's a lot of engineering courses that have dynamics inside them, like vibration and fluid mechanics and all kinds of different things. You know, even thermodynamics has a certain amount of the word name in it. Dynamics. But just, yeah, things are in flux, they're moving. But anyway. Or even the moment that I figured out that A didn't need A. It was a distractor. Yeah, it happens in real life too, right? You get distractors. I get distractors all the time. Anyway, I think we're done, right? I hope this was useful to you in some extent, and we'll prepare you for the homework. I hope you have very happy, fun, relaxing spring break. Anybody going to someplace cool besides home? Home's cool. Home station? No, what do they call that? Staycation? If you stay home? Something like that. I wish I was going someplace proper. Except to that airport park. Don't care for other people. Just don't like it. And now that's down.